Awe-inspired. Look at the Meghalayan Plateau in northeastern India. It is a landscape defined by towering limestone ravines and incredibly dense rainforests. It is also one of the wettest places on the planet. Every year, more than 11,000 millimeters of rain slam into these slopes. That immense volume of water transforms quiet streams into raging, kinetic flash floods in a matter of hours. When modern civil engineers try to connect villages across these expanding rivers, they rely on standard industrial tools. They build with steel and concrete, prioritizing structures that can be driven over the moment the cement cures. But the environment pushes back. The intense humidity accelerates rapid oxidation and chloride-induced corrosion, rotting internal reinforcements. Within a few decades, those rigid spans are frequently shredded by monsoon-swollen rivers. The industrial approach applies a rigid, static timeline to a dynamic environment. By attempting to completely resist the sheer force of the plateau, these modern bridges guarantee their own rapid collapse. The indigenous Khasi and Jingkieng communities solve this by abandoning dead materials entirely, choosing to build with living biology. This engineering rests on a different calculation of time. The elder who carefully plants the initial sapling on the riverbank knows they will likely pass away before the crossing is mature enough to hold human weight. Anthropologists refer to this practice as indigenous futurity. It is an engineering model that trades instant gratification for generational survival, creating essential infrastructure explicitly for the benefit of people who haven't been born yet. The primary building material is the Indian rubber tree, or Ficus elastica. Unlike a typical tree, it produces thick, pliable aerial roots that naturally reach out to anchor themselves to nearby surfaces. Builders harness this natural behavior by placing hollowed-out betel nut trunks across a gorge, using bamboo scaffolds for temporary support. They then carefully thread the young, tender aerial roots directly through those hollow wooden tubes. These trunks are an organic guidance system, forcing roots horizontally across the gap, shielding sensitive tissue, and feeding the plant as wood decomposes. But reaching the opposite side takes 10 to 15 years of patient guidance to cross and anchor. Establishing this skeletal framework means surrendering human pacing altogether. The community cannot force the bridge to materialize. They can only guide the slow, steady biological growth of the organism. But a few thin roots cannot hold a person. The true structural integrity of the bridge relies on a specific biological phenomenon known as inosculation. When two separate roots are pressed together under intense friction, they create a wound. The plant forms a callus, causing the roots to heal and permanently merge their internal vascular systems into a single, much thicker fiber. Builders weaponize this healing process, weaving new daughter roots into the lattice and packing empty gaps with heavy stones and soil. This material creates intense mechanical stress, triggering the tree to accelerate secondary root growth, producing dense, hardened wood exactly where needed. A conventional suspension bridge starts degrading the second the first truck rolls over it. By guiding a living organism, they've engineered a crossing that converts environmental abuse and foot traffic into the exact mechanisms triggering structural reinforcement. The result is the Jingkieng Jri, or living root bridge. After 50 to 100 years of human guidance, these structures mature into waterproof, self-repairing pathways. Some are over 500 years old and capable of supporting 50 people at a single time. They achieve this load-bearing capacity through extreme structural redundancy. A steel bridge can collapse if one uniform cable snaps. A root bridge is composed of thousands of intertwined fibers, all at slightly different stages of maturity and flexibility, meaning there is no single point of failure. When devastating flash floods tore through northeast India in 2014, the rushing water completely shattered newly built concrete bridges. The ancient living root bridges flexed with the storm surges, allowed the debris to wash through their gaps, and remained largely intact. In an environment defined by relentless weather extremes, absolute rigidity is a fatal vulnerability. To actually survive on a long enough timeline, civil infrastructure requires dynamic biological adaptability. Beyond their physical durability, these bridges offer a template for how we might relate to the distant future. Regenerative design involves more than swapping concrete for low-carbon alternatives. It requires prioritizing the needs of generations living centuries away. We must abandon the ego of instant results and adopt the ancestors' ethic, building worlds we will never see.